Hello students, welcome back to SapphireBlueChemspark. Let us start our today's session, the chapter D and F block elements from inorganic chemistry. The previous session we discussed about the atomic and ionic radii of transition elements, oxidation as well as ionization enthalpies. Today we are going to discuss about the electrode potential of transition element. Electrode potential is a physical quantity that can be measured in terms of E0 values. Here the element that can have the tendency to lose the electron or to gain the electron depends on its tendency. Their oxidizing and reducing power is determined. That is what said to be electrode potential. So usually the determination of electrode potential involves the coupling of oxidation as well as reduction reaction. Such reactions are said to be redox reactions. So in this case, the one element that undergoes oxidation, that is said to be reducing agents, where they are ready to lose the electron and hence their oxidation number can be increased. The other one that may ready to accept the electron, that is said to be reduction, where those elements are said to be oxidizing agents and here they can able to gain the electron as well as there is a decrease in oxidation number. Okay, how these E0 values are determined for an element? That can be done by using standard hydrogen electrode. In this standard hydrogen electrode, the molecular oxygen is oxidized to proton, that is the H plus ion, under the standard atmospheric pressure 1 atmosphere and the temperature 25 degrees Celsius or 298 Kelvin. So here that She hydrogen electrode whose E0 value is found to be 0.00 volt. So based on this value only we will find that oxidizing agent as well as reducing agent. The oxidizing agent usually they have the higher positive values. So those are said to be oxidizing agent. So here we can say the fluorine is the strongest oxidizing agent. And the one which has the largest negative value, that is said to be reducing agent. Here lithium is found to be the strongest reducing agent. And all these elements whose E0 values are found is tabulated in such a way the strongest reducing agent to strongest oxidizing agent. So the reducing power that goes on decreases, but oxidizing power on going down that goes on increases. Such a way only the electrode potential is determined for an element. Here the element that might be a metal or even a non-metal. The trends in M2 plus to M standard electrode potential. Here a di-positive ion is reduced to its metal. Here the electrode potentials are measured as reduction potential only because the standard hydrogen electrode is only taken as the oxidation, that means that anodic cell where there only oxidation takes place, to which whatever the elements is coupled with the standard hydrogen electrode, that makes that cathode of the pair. So cathode should always undergo reduction and hence we are saying the reduction potential for the given element. So let us discuss M2 plus to M standard electrode potential for 3D series. So 3D series we have the element starts from scandium to zinc. The graph is plotted between the elements of 3D series versus E0 of its value, the reduction potential. So here titanium is found to be minus 1.63 and the zinc is found to be minus 0.76. So this is what the reference for which we can say here hydrogen is oxidized to what? H plus ion whose E0 value is 0.00 volt. So the 3D series all elements they have their negative electrode potential except copper that shows plus 0.34 volt. And this E naught value here we are calculating for the di-positive ion. We know when the element loses 2 electron, then there would be the first ionization enthalpy as well as second ionization enthalpy. In these cases, the metal, the solid form is converted into its metallic ion in its aqueous solution. So here a solid form getting converted into the aqueous form of the metal ion. It involves the different enthalpies of sublimation and ionization as well as hydration. What do you mean by sublimation? We have a solid metal. The solid metal has to be converted into its vapor. So, it requires enthalpy of sublimation. And enthalpy of sublimation is always a positive value. And after that gaseous state, from which only we are going to remove the electron. We don't know how many electrons are being removed. So, I have taken in general n number of electron is being lost by the metal. So, the ionization enthalpy should be sum up to nth value. If at all 1 electron lost, that is equal to 1 value. If 2 electrons are lost, there would be the first ionization enthalpy, second ionization enthalpy. So, successively we have to add their ionization enthalpy up to which we are calculating that nth value. Once the gaseous metal ion is formed, it is present in solution, their hydration enthalpy involves. The hydration enthalpy is always negative and the ionization enthalpy is always positive. So, where the ability to form their ions in aqueous solution depends upon their enthalpy of sublimation as well as enthalpy of ionization. The sum of sublimation enthalpy and ionization enthalpy, if at all lesser than hydration enthalpy, then its value will be negative. That value will be negative because I said hydration enthalpy is negative. So, the sum of enthalpy of ionization as well as sublimation, if at all less than, this is a positive value, this is the negative value. When you find the difference, the resulting value will be negative. So, where the hydration enthalpy, the difference of enthalpies of these terms gives negative value, those are able to behave as reducing agent. But one trend we may find it for copper. It shows the unusual values of plus 0.34 volt. But all other elements are exhibiting their negative electrode potential. Why copper alone? It shows positive value. This is because its sublimation enthalpy of copper is found to be 339 kilojoule and its first and second ionization enthalpy is 745 and 1960. So, when you sum up all these values, that goes beyond 2500 kilojoule, but its enthalpy of hydration is minus 2120. As the sum of sublimation enthalpy and ionization enthalpy is greater than hydration enthalpy, that's why it shows the positive E naught value. And this element that could not displace any of these elements from its salt solution. Moreover, this copper that can't able to displace hydrogen from the acid also. So, this is what the unique behavior of copper from the 3D series. And the rest of the element we may find the manganese, it shows extraordinarily higher negative value. This is why, because the manganese actually it has D5S2 system. Upon losing the 2 electron, it changes into D5, the half filled, it achieves its half filled of d orbital, the more stable. And the chromium is minus 0.90. So, actually the E naught value, it goes large negative to less negative. But unexpectedly manganese, it shows once again the large negative value. From this iron, nickel, copper, it goes. When we compare the trend in di-positive ion to metal reduction potential, the manganese and nickel along with the zinc they do not show the regular trend in their values. This is why, because the manganese, after the loss of 2 electron, it achieves the d5 half-filled d orbital. And in zinc also, after the loss of 2 electron, it achieves the completely filled d orbital, which are exceptionally stable compared to the partially filled d orbital. And in the case of nickel, it has very high hydration enthalpy, and hence that value it deviates from cobalt and iron. So we expect the value should go towards, after copper it has to go to the positive value. But after once copper achieves that positive value, once again the zinc, that's value decreases from positive to negative. So this is what explained on the basis of their half-filled, completely filled d orbital along with the very high hydration enthalpy of nickel. That's all the trends in M2 plus to M electrode potential of 3D series. The next one, trends in M3 plus to M2 plus standard electrode potential. A tri-positive ion to di-positive ion. The previous case we discussed about a di-positive ion into metal. Here a tri-positive ion is converted into its di-positive ion. So from this trend we are going to find out which of the ions are stable at their higher oxidation state and which of them are less stable in their lower oxidation state. That can be calculated from their E0 values. For example, if M3 plus reduced to M2 plus, it has to receive 1 electron. So this graph it shows titanium to cobalt, where the titanium 3 plus is reduced to titanium 2 plus. Likewise, every element of the 3 plus state is reduced to 2 plus state. So from this graph we may find that titanium, vanadium, chromium, they exhibit the negative E0 value. Here that hydrogen electrode it has 0 electrode potential, and all other elements they are just lying above the positive, that means that hydrogen electrode potential. So the lower negative values of titanium, vanadium and chromium, that said to be they are stable in their +3 state rather in their +2 state. That's why they have the negative value. So it indicates these are stable ions in higher oxidation state. But when I discuss about the other element, say manganese, iron, cobalt. Manganese, the value is somewhat very high. It achieves about 1.51 volt. This is because in manganese, the Mn2 plus it has a half-filled stable d orbital. But when it changes into Mn3 plus, the stability of the Mn2 plus gets removed because it achieves D4 system. So from this we can say that the Mn2 plus is more stable in its lower oxidation state than its higher oxidation state of +3. The next one. From manganese we have to expect that it has to increasing, but you see the manganese after that iron drops down. So iron here it is in +3 state to +2 state. Here the E0 value of Fe3 plus to Fe2 plus is found to be 0.77 volt. So this said that Fe3 plus ion and Fe2 plus ion, both of them are stable under normal conditions. How these E0 values helpful to identify their stability? See, when the E0 value is larger, then it is said to be more feasible the reaction. More feasible, here reduction takes place, so the metal ion they can ready to accept the electron. That is what we are saying the feasibility of the reaction is determined from the E0 value. So greater the E0 value, greater will be the feasibility of reaction. The one more thing we can discuss. See, we said Fe3 plus and Fe2 plus both of them are stable, and here the value of metal is 0.77 volt. We can compare the feasibility of the reaction with iron and copper. When we compare the E0 values of Fe3 plus to 0.77, so comparing E0 of Fe3 plus to Fe2 plus is 0.77 volt. But E0 of Cu2 plus to Cu is 0.34 volt. So the one with greater positive value behaves as an oxidizing agent and the other one with the lower positive value is said to be an reducing agent. So what happened? Ferric ion that oxidizes copper to copper 2 plus, where ferric ion is reduced to ferrous ion. So higher the E0 values of the metal could able to behave themselves as oxidizing agent. That's all the trends in M3 plus to M2 plus standard electrode potential. The next general characteristics of D block elements is the trends in stability of higher oxidation state. When we discuss about the higher oxidation state, we said the metals D block elements, they can able to exhibit too many number of variable oxidation state. And also we discussed the lower extremes and upper extreme of the elements can show only the one possible oxidation state. The middle of the element, they can exhibit the very high oxidation state. So the metals, they are in their higher oxidation state are stable only with in the form of fluorides as well as in the form of oxides. This is why oxygen and fluorine are found to be the most electronegative element, and hence the D block element 3D series, they can able to form the highest oxidation state only with the fluorine and oxygen as fluorides and oxides. At the same time, we can consider the chromium and manganese. Chromium, it has the oxidation state of +2 to +6. It can show all the possible oxidation state. And manganese also able to exhibit +2 to +7 oxidation state. So here the chromium able to form dihalide, trihalide as well as tetrahalide with all the halogen, but at the same time the pentahalide and hexahalides are found to be only in fluorides, not with other halides. This is because the fluorines are most electronegative, as well as you may find the simplest atom and they do not find the steric effect because of its small size. But all other halogen, when number of halogen increases, they do become large in size and find steric effect, and hence the halides are not stable at their higher oxidation state. Similarly, manganese. Manganese can able to form only dihalide with all other halogen, but its higher oxidation state +3F4 +4 can be exhibited by manganese trifluoride, manganese tetrafluoride only. Actually, the highest oxidation state of manganese is +7, but it does not exhibit Mn(F7). Since manganese oxidation state varies from +2 to +7, this is why, because the fluorine is unable to form pi bond with the manganese, and hence Mn(F7) is not known. But at the same time, manganese is able to form the compound of the type Mn2O7. So the manganese exhibits +7 oxidation state only in its Mn2O7 form. This is why the oxygen atom that can make pi bond or the multiple bond with the manganese. So the two MnO4 group that are tetrahedrally bonded to each other. So in this case, manganese exhibits its highest oxidation state +7 only with oxygen. And the other halides, if at all we say fluorides, chlorides, bromides, etc., suppose if they form in their higher oxidation state, immediately they hydrolyzed to form their oxo acids. Similarly, we said MnF7 is not known, but we have MnO3F. In this case, one of the oxygen, that means manganese, it is exhibiting their +7 state only, but the case in which the fluorine is bonded along with the oxygen in the manganese. When we discuss about the stability of copper halides, the copper 2 halides, all the halides are known, but except copper 2 iodide. This is why, because the copper 2 plus ion present in this can oxidize as iodide to iodine. So, copper 2 plus reduced to +1 state and iodide is oxidized to iodine. This is the reason copper 2 iodide is not known, but all other copper chloride, copper bromide, copper fluoride are known. At the same time, most of the copper 1 compounds are highly unstable. This is why, because the hydration enthalpy of copper 1 is very less. But in the case of copper 2 plus, its hydration enthalpy that compensates with second ionization enthalpy of copper 2 plus ion. Because in the second ionization enthalpy of copper 2 plus, it is found to be 1960 kilojoule. So, the second ionization enthalpy is very high because of it changes from D10 to D9. That's why the hydration enthalpy, the large negative hydration enthalpy is compensated by the second ionization enthalpy of copper 2 plus. That's why copper 1 salts are rarely observed compared to copper 2 salts. And in this case, most of that oxides and fluorides are known with their higher oxidation state because of the large negative as well as the stability of the compound. That's all the trends in stability of higher oxidation states of 3D series. Chemical reactivity and E0 values. Already we discussed about the E0 values that indicates about the stability of ions and their tendency to displace hydrogen from acids. So here the transition elements are mostly electropositive. That means they are ready to lose the electron. But some of them, they behave like less electropositive, whose E0 values are the large positive value or low negative value. So we can say, as these elements are more electropositive, most of them, they have a tendency to displace hydrogen from mineral acid, except copper, because copper has the positive E0 value 0.34 volt and this electrode potential is greater than H plus, hydrogen electrode, and hence copper never displaces hydrogen from the mineral acid, but it can oxidize the acids to water. At the same time, titanium and vanadium, they are passive to the non-oxidizing acids. What do you mean by non-oxidizing acid? Like hydrochloric acid. This acid does not behave like an oxidizing agent. An oxidizing agent, they have a tendency to change their oxidation number. But in this case, the chloride ion, it is in -1 state. They can't able to change into its higher oxidation state or even the lower. So, the HCl acid is said to be a non-oxidizing acid, but the other acids, nitric acid as well as sulfuric acid, they themselves can change their oxidation state of nitrogen as well as sulfur, able to behave as oxidizing agent, but hydrochloric acid, that cannot behave as oxidizing agent, and hence titanium, vanadium, they become passive to hydrochloric acid. Passive means they do not react or that renders passivity to the acid. The next one, E0 values that shows the decreasing tendency of formation of +2 ion. Because we found that the trend is not in regular. We said titanium to chromium increases, then dropped to manganese, and then increases to iron, cobalt, nickel, then still it increases to copper, and then once again drop down to zinc. So the E0 values of 3D series does not show a regular trend. So the difference in their E0 value actually that decreases from large negative to less negative value. That shows the tendency to form dipositive ion also decreases. And the metal which are in higher oxidation state able to behave as an oxidizing agent since they are stable in their lower oxidation state. For example, manganese 3 plus to 2 plus, here it behaves as an oxidizing agent. Similarly, cobalt 3 plus to cobalt 2 plus, that also can behave as an oxidizing agent since both of them are stable at their plus 2 state rather in their plus 3 state. So we can conclude that to understand about that standard reduction potential of transition element, we need to know about their sublimation enthalpy, ionization enthalpy and hydration enthalpy. The sum of sublimation and hydration enthalpy should always be smaller than hydration enthalpy. There we can say the elements are ready to lose the electron as well as their E0 value will be negative. But if their values sum of ionization and hydration greater than hydration enthalpy, and those will behave as an oxidizing agent. And moreover, that hydration enthalpy is nothing but the metal ion that surrounds by water molecule such a way. For example, if I have Mn plus ion, this ion it gets solvated where the oxygen atom of water that can able to move towards, that means pointing towards the metal atom. This is what we are saying solvating effect, during which some amount of energy is being released. That amount of energy is what said to be hydration enthalpy. So the hydration enthalpy of the metal ion that depends only on the charge carried by the metal ion. So this is what we are saying hydration enthalpy, and it is always an exothermic process. So during the solvation effect, some amount of energy is being given out when it surrounds the metal ion. Okay students, let us close our today's session. Today we discussed about that electrode potential of transition series alone, and let us continue the same chapter in our next session. Until then, bye bye.